All right. So far, actually, in the semiconductors discussion, we have seen how the band formation happens in a semiconductor, and there is a very explicit difference between metals and semiconductors in the form of band gap. In metals, we don't have band gap, or there is no energy difference between the valence band and conduction band because we have a continuous band structure. But in case of semiconductors, we have a band gap which is of the order of less than somewhere less than 10 electron volts, where actually electron needs to be excited for them to be participating in the conduction process. In the last class, then we discussed in an intrinsic semiconductor how the concentration of electrons as well as holes varies with the temperature, right? And one important um, one important outcome, or one important conclusion which we draw was that the average energy of electrons in the conduction band, it is actually 3 by 2 kT. The kinetic energy of electrons in the conduction band, it is 3 by 2 kT. This is a very important result because it is very different from metals. We saw that in metals the average energy of electrons is independent or very weakly dependent on temperature. That is not the case here. Just give me a second, somebody is at the door. I'm sorry. So yeah, what I was saying is the average energy of electron in conduction band, it is directly proportional to temperature, and it comes out to be same as what we would have got if we assumed kinetic molecular theory for semiconductors. The reason for that is actually that we assumed Boltzmann statistics for electron distribution in the conduction band, which can be safely assumed because the number of energy states which are available in a conduction band, those are much larger than the number of electrons. So the probability of electrons occupying the same state, or basically not following the Pauli's exclusion principle, the probability of that is very very low. So that is why we can assume for Boltzmann statistics, and because of that we get this result which is very different from what we get for metals. So any questions from the previous class? If there are any doubts? Somebody is unmuted. Can you please mute yourself? Yes. Okay. So if there are no questions, let me move with the with today's discussion. So what we have discussed so far, that is mostly for intrinsic semiconductors. Intrinsic semiconductor means they are pure; they don't have any impurity, right? But semiconductors become useful, or they are useful because their concentration or their conductivity, basically, that can be manipulated by using different techniques, and one of them is actually doping of semiconductors. And when we dope semiconductors, basically we introduce the impurity in a semiconductor material, then they are called extrinsic semiconductor. They are not intrinsic semiconductor anymore. So now we will start with the discussion of extrinsic semiconductor. We can have two types of doping. Like, we know that semiconductors can be of two type, n type and p type, where n type means there will be an excess of electrons and p type means there will be an excess of holes, right? Accordingly, actually, whatever type of semiconductor we want to get, we have to plan our doping strategy accordingly. Same semiconductor like silicon, it can be n type or p type, depending on the different types of doping which we can follow, right? So let us say right now we are discussing silicon, and we have doped silicon with arsenic. As you can see here, there is an arsenic atom in the silicon matrix, in the matrix of silicon atoms. So as we know, arsenic has 5 valence electrons, right? And silicon, in a silicon crystal, every silicon atom is forming bonds with, actually let me get my pointer. Yes, so we know that every silicon atom in a silicon crystal, actually it is forming it is bonded with four different atoms, right? So basically it has four covalent bonds with its four neighboring silicon atoms, right? So what will happen is that when we dope silicon with arsenic, arsenic has actually five valence electrons. One thing actually we have to make sure is that the concentration of arsenic should be very very small. Why we need to do that? Because actually when we have low concentration of arsenic, then we are forcing actually we are forcing arsenic to form four bonds. Basically we are forcing arsenic to substitute silicon atom and form four bonds with its neighboring silicons. Otherwise, if this concentration is very large, then there can be bond formation happening between two arsenic atoms also. There will be a probability of that. To neglect that probability, we need to keep this doping concentration very small. For example, of the order of 1 ppm, 1 parts per million, which means there will be one arsenic atom every 10 to the power 6 silicon atoms, right? So we are forcing arsenic to form four bonds, so that actually one of the electrons which is there in the arsenic atom, it is now sort of free, right? It is an extra electron. It is not really free actually, but it is an extra electron, and that electron will be revolving around arsenic atom, right? Because this atom is still localized at arsenic atom, right? It is still belongs to arsenic atom because it has not participated in any bond formation, right? Electrons get shared only when they form the bonds. In this case, this electron has not formed any bond yet, so that means actually this electron is bonded only to the arsenic atom, and it is basically revolving around this arsenic atom. Now this situation actually looks sort of very similar to an hydrogen atom, right? When we have hydrogen atom, it has actually one electron in the outermost shell, and then this electron is basically revolving around the hydrogen nucleus. Similar sort of situation is happening. Only thing is that in this case nucleus charge is very different in comparison to hydrogen, but that can be taken into account, right? So this situation looks very similar to an hydrogen atom. Now actually if we want this electron to participate in the conduction process, we need to free this electron, right now it is localized to this arsenic atom. To make this electron free, we need to ionize this arsenic atom, which means basically we need to plug this electron out of the arsenic atom, so that then it is free, it is a free electron, right? So this energy which is required, the energy which is required to free this electron from the arsenic atom, that comes out to be very small. You must be remembering that there is a ionization energy expression, right? Minus 13.6 n square by z square by n square, something like that. So from there actually we can calculate this energy which is required to free this electron, or basically to remove this electron from this arsenic atom. That energy comes out to be around 0.032 electron volt, right? Why I am saying this energy is very small? Actually because the energy of the thermal vibrations of the atoms, or the energy of the lattice vibrations at room temperature is approximately of the order of 0.07 electron volt. So that means actually the thermal vibration energy itself is sufficient to free this electron. We don't need to provide any extra energy. Like for example, in case of an intrinsic semiconductor, to excite the electron from valence band to the conduction band, we need a very high amount of energy. We need some sort of energy source like photogeneration, or basically photons. In this case, the thermal vibrations which are happening at the room temperature, they are sufficient enough to excite this electron from, or basically to make this electron free, which means actually this electron which will now has become free, it will go to the conduction band of the semiconductor, right? And once this electron has been freed from this arsenic atom, basically it will result into a free electron and an immobile arsenic atom. or arsenic ion, right? This arsenic ion, actually atom is ionized, it is lacking one electron, so that means this arsenic is actually an ionized atom, and it is sort of immobile. Once this electron has been freed, this becomes an immobile ion in the silicon crystal. We can also look whatever way I have explained so far, we can also try to understand that using the band diagram. So what you can see here is actually this is the conduction band of the electron, right? And these are the energy states of arsenic dopants. As you can see, arsenic atom sites every 10 to the power 6 silicon atoms, right? You know, we are putting very few number of arsenic atoms. The concentration of arsenic atoms is very small, right? So that's why we have we have sort of pictorially we have tried to represent it that they are far away from each other. And these energy states of arsenic we have represented with an energy of ed. D here represents actually the donor, because here actually the arsenic is donating an electron to the silicon crystal. That's why arsenic is also called a donor, right? And these energy states of the donor, they are just below 0.03 electron volt from the conduction band. Why I am saying that is, as I just explained, the ionization energy, once the arsenic is ionized, then the electron which is freed from the arsenic atom, that is free for participating in the conduction process. That effectively means that actually this electron has moved from these donor sites to the conduction band of the semiconductor, right? So these energy states of the donor, these are the energy states of the donor, and this is the bottom of the conduction band. The thermal, when you know there is a finite temperature, because of the thermal vibrations, some of these arsenic atoms basically they will release their free electron, and if actually the some temperature is high enough, all the arsenic atoms will be ionized. We will see that actually in the upcoming slides, the temperature dependence. But you can imagine that if the temperature is low, the arsenic atoms which will be ionized, they will be less in the number. But if we have sufficient temperature, most of the arsenic atoms or all of the arsenic atoms, they will be ionized. That means they would have donated their electron to the conduction band of the semiconductor, right? And this transition happens very easily because of the thermal vibrations of the crystal. Now let us say if we want to define the conductivity of an n-type semiconductor. Nd is actually the concentration of the donor atoms. In this case, for example, the what we were discussing just now, in this case it will be the concentration of the arsenic atoms. Let us say if this donor concentration is much larger than the intrinsic concentration of charge carriers in silicon. Ni, you know that, right? We saw that Ni is actually a material property, as we saw here. Ni is a material property because band gap as well as Nc and Nv, there are material properties, and it also depends on the temperature, right? So if let us say the concentration which we are putting, which we are doping in the semiconductor with, that is much larger than the intrinsic concentration of charge carriers, then effectively we can say that the number of electrons is equal to the number of donor atoms only, right? Because the concentration of electrons, that will be dominated by the concentration of the donor atoms itself, because the intrinsic concentration of electrons is very small. So that's why the electron concentration will be equal to the concentration of donor atoms, and the whole concentration we can get from the mass action law, because NP, the product mass action law, is still valid for even an extrinsic semiconductor. The mass action law is still valid. So that's why the whole concentration we can get from the mass action law, that is equal to Ni square by Nd, right? Then we know that the electrical conductivity, it is basically the contribution of both electrons as well as hole. We can simply put the concentration of electrons to be equal to Nd, and the concentration of holes from the mass action law. And because this number will be most probably very small, we can neglect this particular the contribution of holes in the semiconductor, and this thermal conductivity will be is equal to E times Nd times mu E, right? So this is the approximate, or basically very close to the real situation, where actually the thermal conductivity, sorry, electrical conductivity is actually dominated by the concentration of the donor atoms, right? But actually, as I just mentioned before, at low temperatures, all the donor atoms may not be ionized, isn't it? So in that case, we need to also take into account, because then we cannot actually put the concentration of electrons to be is equal to the concentration of donors. We need to actually, what it will be actually, that concentration of electrons will be is equal to the concentration of ionized donor atoms, and that concentration can be calculated using the probability. If we know the probability of a donor atom, that it is ionized, that is actually given by this Fermi Dirac sort of function. This half comes because of the because actually the electrons, they cannot be occupied, the two electrons in the same state cannot be occupied, so that's why this half factor comes into picture here. But this is the probability of basically finding an electron at a particular energy level. In this case, we are putting that to be donor energy level. We are basically saying that this is the probability of finding an electron. So basically the concentration of ionized donor atoms will be the concentration of donors times the probability of not finding an electron, right? Ionized means basically there is, the electron has been taken out, so that is actually the probability of not finding an electron, right? So that's how then we can actually put this concentration here for calculating the conductivity of n-type semiconductors. Any questions so far? Any doubts? Okay. Similar, and now once we have understood the n-type doping, it is quite similar. The p-type doping is also very similar. P-type semiconductor means actually that there will be an excess of holes. So for, let us say, if we want to make silicon, p-type silicon, then we will have to use the the dopants accordingly. For example, if we use boron has actually 3 electrons in its outer shell. So when we put very small concentration of boron in silicon, we are basically forcing boron to form, basically substitute the silicon atom and try to form basically these 3 bonds, but one bond will be lacking 1 electron, right? And this absence of electron is nothing but a hole, right? And this hole, as we can see here, it will be actually bonded to this boron. It cannot still move, it is not still free for participating in the conduction process, so it will keep revolving around this boron atom unless it's get some amount of energy, so that this hole becomes free, right? That energy, again, as in the previous case, it can be provided by the thermal vibrations of the lattice. At room temperature, that there will be sufficient energy for removing this, or basically to make this hole free for participating in the conduction process. Okay, it will keep revolving. Actually, when I said it will keep revolving around the boron atom, actually it is sort of counter movement of electrons, right? When this hole is moving from this bond to this bond, effectively what is happening is actually an electron is tunneling from this bond to this neighboring bond, right? Through the tunneling of electrons, this movement of hole will continues happening actually, right? But when we provide enough energy through the thermal vibrations of the atoms, then this hole becomes free. Similarly, like in the previous case, in this case also, now actually this boron actually is also called an acceptor, because in this case actually the boron is accepting an electron. It is lacking 1 electron, and when it is doped into silicon, it is accepting an electron. That's why it is called an acceptor. and these acceptor energy levels will be just above the just above the top of the valence band or valence band maximum, right? And this energy level is very small, so that these these holes from the valence band can go there, and these basically the hole from the boron, it can move to the valence band of silicon, right? So for example, here it actually the energy difference is about, for boron in silicon, the energy difference is about 0.05 electron volt, right? And in this case again, we, as we saw earlier, the electrical conductivity, it will be dominated by the concentration of acceptor atoms. For example, in this case, the concentration of boron atoms will be as actually is equal to the concentration of holes, and then we can get this electrical conductivity expression, because we can neglect the contribution of electrons to the electrical conduction, because their number, their concentration is very small. Okay, so here are, some typical examples like phosphorus, arsenic, antimony. All these are actually from the same group in the periodic table, right? They have 5 valence electrons in their outer shell, so they are very commonly used as donors in silicon devices. Similarly, all the atoms with 3 valence electrons like boron, aluminium, and gallium, they are used as acceptors in silicon devices. And their ionization energies, as you can see here, they are mostly of the order of 0.10 to the power minus 2, right? Which is a very small amount of energy. Even at room temperature, there will be certain concentration of both of these donors and acceptors, that they will be ionized, right? So that's why these particular donors and acceptors are used. We cannot use donors and acceptors for which the ionization energy will be much larger, because in that case they will not be of any use, right? They will not donate or accept electrons, for so that we can manipulate the concentration of charge carriers. There are particular atoms, there are certain atoms or certain elements which are used as dopants in silicon devices, and that depends on this ionization energy. There is also something called compensation doping, because so far what we discussed was that we are using only one type of doping, like either it is n type or p type. We are using only one type of dopant. But in some cases, if we want to manipulate the concentration of both electrons as well as holes, then we can use the like both types of dopants, like both acceptors as well as donors, which can be present. In those cases, as you know, it is very intuitive. We can again define the electrical conductivity. Let us say, if we have more donor, the donor concentration is larger than the concentration of acceptors. In that case, let us say if this difference nd minus na is much greater than ni, then we can approximate the concentration of electrons by this difference, and from mass action law we can get the whole concentration. And then we can simply use both they both actually, in this case we cannot assume that the whole concentration or the contribution of holes will be negligible. In this case, we need to take into account both the electrons as well as holes, the electrical conductivity coming from both electrons as well as holes. Similarly, there will be scenario for when we have excess of acceptors in comparison to donors. We can define again hole concentration and electron concentration, and we can use them in the expression for electrical conduction, right? So this is called compensation doping. When we have both donors as well as acceptors present in the semiconductor, then we call it as compensation doping. Okay, any questions? Any questions so far? There is a question. There is a question from somebody is asking from chapter 4. I would suggest that you ask this question during the tutorial, because yeah, I mean, if I start discussing that, then it will break the flow of the lecture itself. Okay, so I mean, you can either send me this through email and I will answer your question, or otherwise you can also ask it uh, during the tutorial. Okay. So, if there are no questions on this, let us move towards the temperature dependence of conductivity. How conductivity varies with temperature. So we know that, right? The let me just sigma is equal to Ne times nu dE plus, right? So charges, this is the charge of the electron and charge of the hole. They don't vary with temperature. We know that these charges will remain the same as a function of temperature, but concentration of electrons and holes, as well as the drift mobility, they can change as a function of temperature. So we will actually start this discussion by individually first discussing how the concentration of charge carrier varies with temperature, and then we will discuss how the mobility varies, drift mobility of electrons and holes, that varies with temperature. All right. So carrier concentration as a function of temperature. Usually there are three different temperature regimes which define sort of temperature dependence of carrier concentration. What happens is that if temperature, let us say if the temperature is very small, we have already discussed a little bit, but when the temperature will be small, all the donor atoms, they will not be ionized, right? There will be only few donor atoms which will be ionized, right? So that means the and actually at low temperature, even the intrinsic concentration will be very low, right? Because intrinsic concentration means actually we need to excite the electrons from the donors to the acceptor, right? So we need to, in this particular case, the carrier concentration will still be dominated by the concentration of the donors, but all the donor atoms will not be donating their electron to the conduction band. There will be only a fraction of the donor atoms which will be participating in the conduction process, or which will be donating their electron in the conduction band of the semiconductor, right? So then what will happen, there will be a particular temperature where actually all these arsenic atoms or all the donor atoms, they will become ionized. This temperature is also known as saturation temperature. This Ts is actually the saturation temperature. Okay. At this saturation temperature, basically all the donor atoms which are there, they will become ionized, right? So what will happen is that in this temperature range, between at medium temperature range, all the arsenic atoms, they have ionized and they have donated their electrons to the conduction band. So from a certain in this temperature range, so the concentration of charge carriers or the concentration of conduction electrons will remain more or less constant, because actually all the donor atoms, they have been ionized already. So this concentration, basically the concentration of electrons, that will be is equal to the concentration of the donor atoms. So this concentration will remain constant in this medium temperature range, where we have actually crossed the saturation temperature, but we are below a certain temperature. Actually this is Ti. This is also known as intrinsic sort of Ti here represents actually intrinsic, because what happens is that above this temperature, when the temperature is greater than a certain temperature, the electrons from the valence band, they start getting excited to the conduction band. The transition from valence band to the conduction band, there is enough energy in the thermal vibrations because of the increase in the temperature, so that the electrons can be excited from the valence band to the conduction band, right? And then the concentration of electrons is actually dominated by these intrinsic electrons. By intrinsic electrons, what I mean is that the electrons which are coming from the valence band, the concentration, the total concentration of electrons is actually dominated by these intrinsic electrons now, right? So basically we can say that there are three different temperature regimes where concentrate the where actually the carrier concentration depends, varies differently as a function of temperature. At the lower temperature, because all the donor atoms, they are not ionized, basically, just give me a second, I will ask these guys to stop this for a second. Okay, so we have three different temperature regimes. At the lower temperature, all the donor atoms are actually, they are not excited, or basically they have not donated their electrons. The probability of this donation actually will depend on this temperature difference, right? This delta E, it will depend on the it will depend on the energy difference between the donor levels and the conduction band minimum, right? The number of electrons which will be donated by the donor atoms. In the medium temperature range, when actually the temperature is above the saturation temperature, all the donor atoms have been ionized. That means they have donated their electrons to the conduction band, so they will all participate in the conduction process. So in this temperature range, actually the concentration of charge carriers, or the electrons in this case, remains the same, remains the constant. Above the intrinsic temperature, the concentration of electrons is dominated by this by the electrons which are getting excited from the valence band to the conduction band, right? So in this temperature range, actually the semiconductor starts behaving as if actually it is an intrinsic semiconductor, because the concentration of electrons is coming through the excitation of electrons from valence band to the conduction band, which happens in the intrinsic semiconductor. So now if we can look at this plot where actually the concentration of electrons is plotted on a logarithmic plot, and on the x-axis we have inverse of the temperature, right? Inverse of the temperature means here it is from, the temperature is from higher to lower on the x-axis, right? So let us start from the lower temperature, where actually the conduction, or sorry, the charge carrier concentration, it is dominated, or it is determined by the ionization of the donor atoms. So in that case, the slope is actually is equal to minus delta E by 2k, because this delta E, this delta E is actually the difference between the donor energy levels and the conduction band minimum, right? This delta E is actually the concentration of, sorry, the energy difference between the donor energy levels and the conduction band minimum. And although this this NC and D, let me, if you remember, the concentration of electrons in a intrinsic semiconductor, it is defined by this particular expression, right? Here we have NC NV times exponential minus Eg by 2kT. We have actually derived this expression also from here only. In this case, what happens is actually the electrons are excited from the valence band to the conduction band. So we had actually taken the density of states in the conduction band and valence band, and that is multiplied by the exponential of energy difference. This Eg is actually the band gap, right? Because in this case it is taken as band gap because actually electrons are excited from valence band to the conduction band. In this particular case, what will be happening is that here actually the electrons are getting excited from the donor levels to the conduction band, right? So that's why we have replaced this NV here by ND. This is actually the donor energy levels, or the density of states at donor energy levels, and this NC is actually same, which is here also, right? And again we have to replace this band gap by delta E, because now the electrons are getting excited from the donor energy level to the conduction band. So actually this expression is derived from this expression only. All right. So this, although actually the NC depends on temperature, right? But this exponential dependence is much stronger. So that is why the slope of this part, actually it is defined by this exponential part only. If you remember, the NC concentration actually depends. If you look at here, NC is, where is NC? Yeah, it depends. It actually varies with temperature as T to the power 3 by 2, but this exponential dependence comes out to be much stronger. So that is why the exponential dependence which is here, that is much stronger than T to the power 3 by 2. This actually depends on T to the power 3 by 2, but this is much stronger, right? So this, the slope of this part will be minus delta E by 2k. In the medium range, as we just discussed, the charge carrier concentration, it remains same, and actually it is equal to the number of donor atoms, right? And this is known as extrinsic range, and this is actually the most interesting range also, because this is the temperature range which is utilized in PN junctions, because we actually want to donate, we want to uh, minimize the donor concentration, as we just discussed, right? This 1 by 2 came actually because this 1 by 2 here, right? Because the, as we just saw in the probability, where was it, here? So this, because there is 1 by 2 expression here also, the probability of finding an electron in the donor energy level, it is different, it is slightly different than the intrinsic semiconductor. So that's why this half factor appears here also for the same region, because actually the energy states or the probability of occupation is slightly different in case of donor atoms. Why is it different? That is not of really interest as of now. So we can just, we can ignore why this difference is coming, because that does not make any difference to our discussion, right? So but this half comes because of difference in the probability distribution function in the donor atoms. Okay, so this, yes, we were discussing this extrinsic range. So this temperature range is actually more important, because as I just said, we want to minimize the donor, the doping concentration, so that they are forced to mingle in the silicon crystal. And if we want to do that, we need to utilize all the donor atoms which are there, right? And they are utilized only in this range. In this range, all the donor atoms, they are not donating their electrons, so actually they are not, all of them are not participating in the conduction process. In this range, the charge carrier concentration actually is dominated by the intrinsic concentration of electrons, right? All the electrons, or actually the concentration of electrons, it is dominated by this excitation process from the valence band to the conduction band. Only in this range actually we are able to utilize the full concentration of dopants which we are using in our semiconductor. So that is why this extrinsic temperature range is actually of the most interest when we discuss about semiconductor devices. Again, in this case, this slope is much steep. It is much steeper than the first part, because this band gap energy is much larger, right? So that is why we have much steeper curve here in comparison to the first part. And this temperature range is actually known as intrinsic semiconductor, because all the electron concentration is dominated by this excitation from valence band to the conduction band. There is a question: how are we defining slope for an exponential function as it defined for a straight line? Okay, you got it already. Yes, because we are plotting actually a logarithmic plot, right? So that is why we can define it by the straight line. Any questions on this? I think it is very intuitive, but very interesting also, because we can visualize almost what is happening at low temperatures. All the ions are not ionized, then all the atoms are participating, and then at higher temperatures the process itself or the concentration of electrons is dominated by a different process. Again there is a question. Sir, in intrinsic part there are electrons that are excited from valence band also and from donor atoms also. So there are more electrons, so it should be more beneficial because we would be getting more current then. Yes, actually, I mean, see, that depends on the application of your device. If if your device is going to be used at these high temperatures, and if we want higher current, because see, high current is always not desirable in some devices. Actually, there is a current range which is desirable in every device. So if your application is such that it is going to be that your device is going to be used at higher temperatures and you need a very high current, then yes. But actually even in those cases, because see, the thing is, in this intrinsic range the concentration is dominated by this intrinsic process only. So the donor atoms, the concentration of electrons which are coming from donors, that becomes negligible after a certain temperature. So that means they will not make any difference. So we don't need doping itself. Like for example, the amount of electrons which you will be getting from the donors, probably you can get that by increasing the temperature by very small amount. So that's why actually this is not really in this range. Actually the intrinsic concentration, sorry, the extrinsic concentration which is coming from donors, that is not being actually utilized, because the concentration of electrons, it is dominated by the intrinsic process only, right? And I mean, your question is, I can understand, but it depends on the application also. But I mean, I would not say the donor concentration is being utilized in this case, because then the conductivity is actually defined by the intrinsic concentration only in this in this part of the graph. Okay, any other question? Here this is actually what we are plotting here is actually intrinsic concentration. Again, this is a logarithmic plot versus 1000 by t. So as you can see, this is only the intrinsic concentration, like in an intrinsic semiconductor for silicon, gallium arsenide and germanium. This is how the plot looks like. From this slope actually we can get the band gap, right? Because it will depend on the band gap, right? This intrinsic concentration depends on the band gap. So we can get the band gap from here. And also one another use of this particular graph can also be that at a particular temperature, what will be the intrinsic concentration. We can know that what will be the intrinsic concentration, and from there actually we can see whether the concentration is being dominated by the intrinsic concentration or by the extrinsic concentration of charge carriers which are coming from the dopant atoms. So this plot for the intrinsic concentration, which is actually much easier to get, that can be used for seeing which in which range we are operating in at a particular temperature. So that this kind of intrinsic plot we can use for that particular purpose. Okay, so I mean, yeah, this is the temperature dependence of charge carrier concentration. If you have any questions, we can take them up now, or yeah, I think we will start with this dependence of drift mobility on temperature in the next class. So yes, please go ahead and ask. I mean, if you have any doubts, we can discuss them now. Any questions?